What do you see?
Sand.
Imagine if we could look so closely, we could see each grain, each particle. You see, there are patterns in everything.
Integrals, infinite series.
I've never seen anything like them. From an Indian.
From Hunter College. My name is Abunawat Berry, and today we're doing lecture number 19 of real analysis. Today we're doing functional limits. So now, last time you may recall that we actually defined the limit of a function using the epsilon delta definition. Now, let's actually make that formal. So let's say we have a function, f of x, which looks something like this. And we have certain x value a. And we say that the limit as x approaches a of f of x is equivalent to L. Maybe L is this right over here. If and only if for all epsilon is greater than 0, there exists a delta also greater than 0, such that if 0 is less than x minus a, which is less than delta, then f of x minus L has to be less than epsilon. So this is the definition of a functional limit. So now, how does this have any similarity to what you probably learned informally in your Calculus 2 class? Well, let's look at it. You have the delta neighborhood of a right over here. The distance between x and a is greater than 0, which means x is not equal to a, and less than delta, which means x is somewhere within this neighborhood between a minus delta and a plus delta. And then you want to make sure every single point in there maps to some point in the epsilon neighborhood of L. So if for all epsilons that exist around here, there is some delta that corresponds to it. This means that x is not equal to a, and x lies somewhere within this delta neighborhood. So then we have the minimum right over here. So we want to make sure every single point in this neighborhood that's possible, which is every single point in this range, will map to some point in the epsilon neighborhood. So a possible epsilon could be something like this. So we just want to make sure for all, let's say n, or for all, n is a good enough number or variable. For all n, which is in the delta neighborhood of a, f of n has to be in the epsilon neighborhood of L. Alright, so more formally, what does this mean? Well, this is as formal as we can get. So what are some corollaries that we can take from this? Well, how do we want to prove that a function converges to L? That can be done via sequences. You see, if we have a sequence xn, x1, x2, x3, x4, and why are we using sequences? Well, we already have the notion of a limit for sequences. So of course, when we're trying to talk about functional limits, it has to relate back to our notion of limits for sequences. So we get x1, x2, x3, x4, dot, dot, dot. So that means that the limit as n approaches infinity of xn has to be equal to that number a. So let's draw that on our whiteboard. We have our function, and then we have a, and we have some sequence, x1, x2, x3, x4, what it actually looks like doesn't matter. It just has to be with elements taken from the domain of the function. x1, x2, x3, x4, x5, x6, so on and so forth. And so, this sequence will converge to some limit on the x-axis, and we want to show that the limit as n approaches infinity, f of xn is equivalent to L. Now, how do we know when a limit doesn't exist? Ooh, this is a gloppy glop. Well, remember how we said that if we have a sequence, so if we have x1, x2, x3, x4, x5, x6, and so on and so forth, let's say we take a certain subsequence, xn1, xn2, xn3, xn4, dot, 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 and then let's say we take a second subsequence, xa1, xa2, xa3, xa4. So if xnk approaches limit L1 and xak approaches a limit L2 and L1 is not equal to L2, then that means that the sequence xk does not approach any limit. So, in the same way, we can say a very similar thing for functions. So, if xn approaches a and yn approaches a, but the sequence formed by this approaches L1 and the sequence formed by this approaches a limit L2 and L1 is not equal to L2, then the limit does not exist. So let's think about an example. We've already seen the Dirichlet function before. The function that is 0 if you're an irrational number and 1 if you're a rational number. So it's just going to be a sprinkling of dots at 1 and a different sprinkling of dots at 0. So, how can we prove that it has no limit anywhere? Well, to start, let's say we have some point A right here. So, we want to form a sequence xn that converges to A and another sequence yn that converges to A. Alright, so I've got an idea. Let's say xn is equal to the A of accurate to n decimal places. So how can we say this? So xn is, so for example, if A is 1.359267 dot dot dot, then x1 is equal to 1.3, x2 is equal to 1.35, x3 is equal to 1.359, x4 is going to be 1.3592, x5 is going to be 1.35926, so on and so forth. So hopefully it's pretty easy to see that xn is rational for all natural n. So now, what about yn? Well, I've got a very nice proposal. Yn just equal to xn plus pi divided by 10 to the n. Now here's the thing. Pi is irrational. Since pi over 10 is just moving everything one digit over to the left, pi over 10 is also irrational. So is pi over 100 and 1,000 and 10,000. But this term is getting smaller and smaller as n approaches infinity, so we can say this still approaches the same limit as xn, which is a. So we've shown xn approaches a and yn approaches a. Because there exists some n, so given any epsilon greater than 0, there are just some natural n such that for all little n greater than capital N, greater than or equal to capital N, xn minus a is less than epsilon, and yn minus a is less than epsilon. Or if you really wanted to, you could write two separate statements, but I'm not really going to do that here. So that works, right? Now, let's show that f of xn and f of yn converts to two completely different things. So let an be f of xn and bn be f of yn, right? So now, what do an and bn converge to? Well, let's figure it out. F of xn is obviously going to be equal to, well, what's xn? It's rational for all n, as we've seen over here. And what happens when we plug in a rational number? Well, the Dirichlet function says that it's 1 if x is rational and 0 if x is irrational. So that means f of xn should be 1 for all xn because xn is rational for all xn, for all n. Sorry. Alright. And in a similar fashion, f of yn is equal to 0 for all n because yn is in Q complement, or the irrational numbers, for all n. So that means that even though these two converge to the same limit, their functional limit, the functional limit doesn't exist because the limit of these two sequences within the function are different. So they both approach a, no matter what a is, but one will approach 1 and the other will approach 0. Since 1 is not equal to 0, that means that the limit of the Dirichlet function doesn't exist. But wait, since the limit of this is 1, but the limit of this is 0, even though they converge to the same limit, 1 is not equal to 0, which means we've proved that for all a in the real numbers, the Dirichlet function is discontinuous. This thing is completely discontinuous, literally everywhere. But can we prove that the limit doesn't exist for a continuous function? Let me give you an example. This is what we call the Topologist curve in formal mathematics. Or if you're one of my classmates, you call it the freaky function. So this is the function f of x is equal to sine x to the minus 1. So what does that look like? Well, x to the minus 1 is 1 over x. So let's think about some values that this could be. So if x was equal to 10 to the 9, 1 billion, then that would mean 1 over x is almost equal to 0, which means sine of 1 over x should basically be equal to 0. So we at least know that the limit as x approaches infinity, sine 1 over x has to be equal to 0. Just a hunch, right? But now I'm going to ask you a critical question. What's the limit at 0? What's the limit as x approaches 0 of sine 1 over x? Well, once again, we have to construct two sequences within this function. So what do we do? Well, let's graph it. So it chills out over here, then it gets a little slimmer, Then it gets even slimmer than that, and it gets even slimmer than that, and that, and that, and that, and that, and that, and eventually it becomes an unintelligible mess in the center. At 0, we still don't know the limit, so we'll leave that blank. And then kind of after going like this for a while on the other side, it finally cools down and cools off. And it approaches 0 again on this side as well. So yeah, that's what the topologist curve looks like. Pretty cool, right? Now, if you try and zoom in to find out what 0 is on a graphing calculator, your graphing calculator will probably break because it's not meant to handle this many lines. So, instead, how can we prove that this actually doesn't have a value? That's right, there is no limit as x approaches 0 of sine 1 over x. Now, why are we allowed to even talk about this? Well, let's think about it. The domain of this whole thing, the domain is just the real numbers, but without 0. Why without 0? Because you can't divide by 0. But 0 is still a limit point of this set, which means we can still talk about the limit as x approaches that point, because there exists some subsequence, in fact, infinitely many subsequences, that converge to that exact point. So, we've got xn approaches 0 and yn approaches 0. So now, what could xn and yn be to mess this stuff up? Well, we want f of xn to not be equal to f of yn as n approaches infinity. So we can try the same trick we did last time. Here, we could be very easily assured that what the limit was, because it was the same for all n in the sequence. This was just 1, 1, 1, 1, 1, 1, 1 for all n in the sequence. This was just 0, 0, 0, 0, 0, 0, 0 for all n in the sequence. So, we're going to try and do the same thing here. We're going to try and make one of these all 1s and one of these all 0. X equal to 1. Well, that's when x is. Let's draw a graph to remind ourselves. That's when x is equivalent to pi over 2 plus some integer multiple of 2 pi. And when is sine of x equal to 0? Well, that's when x is equal to some integer multiple of pi. So now, let's write 1 over these, so that once we plug these in, we can actually get what's inside back. So we get 1 over pi over 2 plus 2k pi is xn, or xk, I guess, and yk is 1 over k pi. Pretty simple, right? So now, how can we prove that f of xk and f of yk approach different values? Well, let's think about it. First, we need to show they actually approach the same value, xk and yk, and that value being 0. And it should be pretty obvious just from what you can see here. We've already shown many times in the past that anything of this form, 1 over some constant times x plus some other constant which doesn't have an x attached to it. In fact, 1 over any one of these polynomials, this always going to be approaching 0. So, what do we do in this case? Well, this is just another one of these types. Got 1 over pi over 2 is our constant, plus 2 pi is our coefficient, and then k, x. This is just the exact same thing rehashed. This approaches 0, and this approaches 0. Why? Well, k pi is always increasing, and pi over 2 plus 2k pi is always increasing, which means that their inverses are always decreasing. But they can never be below 0 because k pi, pi over 2 plus 2k pi are always positive there. So that means that these two both have to approach 0. So then, what do we do after that? Well, we show that f of xk and f of yk approach two different values. It should already be pretty obvious. We've designed xk and yk such that for all k, f of xk is just going to be 1. So that sequence is going to be 1, 1, 1, 1, 1, 1, dot, dot, dot. And of course, the limit here is just going to be 1. And the same thing, f of yk sequence is going to be 0, 0, 0, 0, 0, dot, dot, dot. And that's just going to approach 0. So we know xk approaches 0, yk approaches 0, but f of xk approaches 1, while f of yk approaches 0. Thus, the limit as k approaches infinity, or rather, the limit as x approaches 0 of sine 1 over x does not exist.